Welcome to the deep dive. Today we're heading inwards, really close to the sun, to look at Mercury.
The smallest planet, the fastest one.
Exactly. And it looks, well, it looks a bit like our moon, doesn't it? All rocky, cratered.
Very moon-like at first glance. And the temperatures are just wild.
Totally extreme. Scorching hot days, freezing cold nights, long wings too.
Right. But beneath that unassuming surface, there's a really big puzzle, a major structural mystery.
Okay, you mentioned a mystery, something hidden deep inside. What's going on with Mercury's core?
Well, that's the thing. Its core is huge. I mean, disproportionately enormous.
How big are we talking? Compared to, say, Earth?
Okay, so picture this. Mercury's metallic core, its iron heart, takes up about 85% of the planet's entire radius.
85%. Serious.
Seriously. Compare that to Earth. Our core is, what, about half our radius? Maybe a bit more.
So Mercury is almost all core.
Pretty much. It's like if you could peel Mercury like an orange.
Yeah.
You'd find this tiny, thin layer of rocky peel and then this massive metal fruit inside.
Wow, that orange analogy really helps picture it. That's fundamentally different. How does a planet even form like that?
Well, that's the multi-billion-dollar question, isn't it?
Yeah, I guess so.
Our standard models of how planets form, they don't easily spit out a world like Mercury. That massive core-to-mantle ratio is just odd.
So something unusual must have happened.
Something pretty dramatic, yeah, either during its formation or very early in its history. Something violent or at least extreme.
Okay, so that's our mission for this deep dive then,
Yep.
to unpack the theories.
Exactly. We're going to look at the main ideas scientists have come up with to explain Mercury's giant iron heart.
All right, let's get into it. What's the first big theory?
Well, the most, let's say, cinematic one is called the hit-and-run hypothesis.
Hit and run. Sounds dramatic, like a cosmic collision.
Precisely. The idea is that young Mercury wasn't always like this. It started out bigger, maybe more like a standard rocky planet with a more normal ratio of rock to metal. Then, very early on, maybe billions of years ago, bam, it gets hit by another massive object, something planet-sized or maybe a large protoplanet.
A giant impact. A bit like the theory for our moon's formation.
Similar kind of event, yes, in terms of the scale of the collision, but the outcome here was different for Mercury itself.
How so?
The impact was incredibly powerful, so powerful that it didn't just create debris. It literally stripped away most of Mercury's original rocky mantle and crust.
Just blew it off into space.
Blew it off, blasted it away. What survived the impact was mostly the dense, heavy metallic core, maybe with just a thin coating of the original rock left clinging on.
Wow. So it's like the survivor of cosmic mugging, left with just its heavy iron heart.
That's actually a pretty good analogy, yeah.
Right.
A cosmic stripping event. And there's some thinking that its surface composition, maybe even its rotation, could hold clues pointing towards this kind of catastrophic past.
Okay, that's definitely a dramatic explanation. What else is on the table? If it wasn't a giant whack.
Another idea points the finger not at another planet, but at the sun itself.
The sun. How could the sun do that?
This is the solar vaporization theory. You have to remember, the early sun, when the planets were forming, was way more active and hotter than it is now.
Right, a much more energetic young star.
Exactly. And Mercury is incredibly close. So this theory suggests that the intense heat and powerful radiation pouring off the young sun literally boiled away Mercury's outer layers.
Boiled away. The rock just turned to gas.
Essentially, yes. The lighter silicate rock, the stuff making up the crust and mantle, it just got vaporized by the extreme heat. And then the strong solar winds, which were also much fiercer back then, would have just blown that rock vapor away into space.
Leaving behind
The heavier, more resilient materials, primarily the iron core, which could withstand the heat better.
That sounds pretty wild too, but I guess it makes sense given the location. Do we see anything like that elsewhere?
We do, actually. We observe young star systems now where planets orbiting very close seem to be losing their atmospheres or outer layers due to their star's activity, so it's a plausible mechanism.
Okay, so theory 1, giant impact strips it. Theory 2, the sun cooks off the outer layers. Is there a third option, maybe something less violent?
There is, yes. A less dramatic possibility. This theory suggests that Mercury didn't become this way through some later event. It just formed like this.
It was born different.
Kind of, yeah. The idea is that it formed in a very specific part of the early solar nebula, that big cloud of gas and dust where everything came from.
And this part of the cloud was special how?
It might have been unusually rich in iron and other heavy metals. right from the start.
But wasn't the nebula generally mixed? How would you get an iron-rich zone right there?
Well, the young sun's magnetic field could have played a role. Think of it acting like a giant sorter.
Okay.
Its magnetic forces might have drawn the heavier metallic particles inwards towards the sun, while lighter silicate dust got pushed or stayed further out. It's about how materials condense at different temperatures and react to magnetic fields.
So Mercury just happened to form right in that sweet spot, that iron-heavy region.
That's the idea. It just accreted from material that was already disproportionately metallic because of where it was in the nebula. No catastrophe needed, just location, location, location.
Huh. So it wasn't a victim. It was just a product of its environment from day one. That's really interesting.
It is. It highlights that maybe not all planetary oddities need a cataclysmic explanation. Some might just be down to the initial conditions of formation.
So we have the three main ideas: the giant impact, the solar bake-off, and just forming differently in an iron-rich zone. Where do scientists land now? Is there a front runner?
Well, that's where it gets tricky. There isn't really a definitive answer yet.
Still up in the air.
Very much so. Each theory has points in its favor, but also challenges, things that don't quite fit the observations perfectly.
Like what?
Well, for example, the impact theory needs a very specific kind of collision to strip the mantle without completely destroying Mercury. The vaporization theory struggles sometimes to explain the presence of certain volatile elements we do still see on Mercury's surface, things that should have boiled off easily. And the formation theory needs the nebula conditions to be just right in that specific location.
So no easy answer.
No easy answer. Scientists are hoping that ongoing missions like Bepi-Colombo, which is orbiting Mercury now, will give us more detailed data on its gravity field, its magnetic field, its surface composition to help test these ideas.
Right. More data needed.
Always more data. For now, Mercury remains this stubborn puzzle, this tiny little planet with this absolutely enormous, mysterious heart.
A tiny planet with a giant heart. It really underscores how much we still don't know, even about our closest neighbors.
Absolutely. It's a fantastic reminder that the solar system's past was likely far more dynamic, chaotic, and maybe unpredictable than we sometimes imagine. These planets hold secrets about their formation and evolution.
It definitely makes you think. So the final question for you, our listener, to ponder: what does Mercury's strange, oversized core suggest about the wild processes that shaped our own solar system and maybe countless others out there? How many other hidden histories are locked away inside these worlds, just waiting to be uncovered?